Okay, could you please close the door? Okay, so then in the next hour, I think what we're going to manage is to talk about Euler's formulas that establish the relation between the exponential and the sine and the cosine by means of complex numbers. So that should be possible. And then I think we can actually get to the complex Fourier series by focusing on the main steps. So we can get that done today, I think. So that's then the plan for the remainder of statistical data analytical methods today. So Euler's formulas. So the crucial thing about the whole thing with Euler's formulas is what I told you previously, so that the exponential function with a complex argument, which is also called a complex exponential, is the same as the cosine of the x plus I sine x. So remember that x, ix, that's how I write it, because I mainly also write it in probabilistic modeling, the exponential function in an applied context. This is also often written as e to the power of ix. It's the same thing. So that's what is called the first Euler formula, or at least it's one Euler formula. Now if you multiply I with -1, so you put a -1 in front of the I, then what happens here is that the sign changes. So you just have a -1 in front of the I, which then you also have on the right hand side. Yeah, and at least to me, this is surprising that this holds. So that if you have the exponential function and you put something a complex number into it, then that you get to cosine and sine. It's somewhat surprising. One can also es auf die Spitze treiben. One can also make it even more surprising if one, for example, chooses x equals pi. In this case, what we would get is x times pi, I pi, equals cosine of pi plus sine plus I sine pi. And so if you think about the cosine and the sine function, so cosine and sine, and here you have 2 pi, so here you have pi, and then you see that at pi, if you put pi into cosine and sine, you get for cosine you get -1, and for sine you get 0. So if you put the -1 then on the other side, what you get is that x I pi plus 1 equals 0, or even more shorthand, e to the power of I and pi times pi, plus 1 equals 0. And that's called Euler's identity, and that's fairly surprising, I would think, at least under certain conditions. Of course, surprise always depends on your model of the world, and depending on your model about these numbers, this may be more or less surprising. So the surprise here in a way is that you have 3 fairly fundamental numbers in math. So e, the exponential number or Euler's number, I, the complex unit and pi, and they are all related and come out in this equations, which is just a specific case of Euler's formulas. So the bigger question is, why do Euler's formulas hold? And this is what I want to go over now. So essentially show a proof of why these Euler's formulas hold. So these are Euler's formulas, because Euler's formulas, like I said earlier, I mean, they will be immediately important when we talk about the complex Fourier series, but they will also be long-term important when we talk more about the MR image acquisition process. So it makes sense to invest a little bit there to understand how they come about. On the other hand, how they come about is also fairly straightforward. So let's just do it. And the essential trick to prove Euler's formulas, proof of Euler's formula, and I'm focusing on the first one here, while the other one essentially only needs a minus sign somewhere, so I'm actually not quite sure whether one needs to prove it really. Proof of Euler's formula. The proof just is based on the series representations of the exponential, the cosine, and the sine functions. And if one is happy with these representations, which we've seen also previously, then also the proof in Euler's formula is actually quite trivial. So the whole thing then follows from these series definitions of the complex, not of the complex, of the exponential, of the sine and the cosine function. And then the bigger question is why these definitions hold or whatever. That doesn't make sense, this question. So then one should just congratulate the inventor of these definitions for great definitions and go home or write a paper or something. So this is what we've seen before. So the exponential function is defined as this infinite sum of these terms. So if you have x and you put it into the exponential function, what you need to compute to evaluate the exponential function is to take x to the power of n divided by the factorial of n multiplied by -1 to the power of n. No, that cannot be. No, that's a -1 too many. That's bullshit. It's just this. Sorry, that's a copy and paste error. Because the cosine and the sine functions are defined like that. So you need to put x, take x to the power of n divided by the factorial of n, and do that for all n going from 0 to infinity and add them all up. Of course, you can also maybe stop this, I don't know, for n equals 100 or so. Maybe do that as a little programming exercise and compare to the output of MATLAB's exponential function. Then you see how good it is if you use a truncated exponential series. The cosine and the sine are defined fairly similar. However, they actually have this -n, -1 to the power of n. Factor n there. So remember that the cosine used the, if you want to call it that, the even numbers. There's some typos in there. I have to remove some typos. So that's 2n and then the factorial, not 2n and then factorial. That's 1 minus x squared. So we only deal with, so when n goes up now from 0 to infinity, we only see the even terms here. So x squared, then divided by 2, so that's the case when n equals 1. If n equals 2, then we have -1 to the power of 2, so So that's a positive number. Here n was, so maybe let's write this here, n equals 1, n equals 2. Then we get 4, and we have to also divide by a factorial of 4. And then if n equals 3, we have again something negative here because it's minus 1 to the power of 3. And we have 6 here and factorial 6 there, and so on. So that's basically working with the even numbers on in this expansion of the series, or whatever you want to call that. And similarly for the sine function, however, with the odd numbers. And also there it needs to be 2n plus 1 factorial. So if I didn't do the 0 there, let's do it here. If n equals 0, then we have 2 times 0 to the power of n. And to the power of 0 always means 1. So we have 1. And we have here we have 0. So we have, for this thing we have 1. For this we have 0 plus 1, so we have x. And for this we have 2 times 0 is 0 plus 1, so we have factorial 1, which is 1. So we just have x. And then if n equals 1, we have minus 1 to the power of 1, which is minus 1. So we have a negative term, and we get 2 times 1 plus 1, so that's 3. So we have x to the power of 3, and we have 2 times 1 plus 1, so we have divided by the factorial of 3. And then let's do the next one, so that you see this alternating sign. So for n 2, we have minus 1 to the power of 2, so that's plus 1. And then we get to the odd number 5, so we have x 5 divided by 5. And then the next odd number for n equals 3, we get 7. Yeah. So these are little. It's more, or it's actually more programming, or yeah, it's not really programming. It's just little gritty math stuff. Yeah. So that's basically what I just discussed is, okay, that's the definition of the exponential, the cosine, and the sine function in terms of the series, and then I computed written down more explicitly the early terms for n being 0, 1, 2, 3 for all of them. Yeah, that's the only thing that happens. Is a little bit nitty-gritty, especially with the changing sign. But then it's also quite straightforward, because these so 2n just encodes the even numbers, and 2n plus 1 just encodes the odd numbers. Good. So these are just the definitions, and they are just there. So questions about this, or do I have any typos either on the board or in the script? I mean, in the script there are at least 3 already. So the exponential doesn't have a minus 1 times n, and the factorial in the cosine and the sine function needs to be outside the brackets. But I think on the board it's better. So then to get to Euler's formula, what we now consider is actually the left hand of Euler's formula, where you have the exponential and you put in I times x. So again, there's this typo. So if you see a typo many times, maybe it's not a typo, but I think it's a typo. Because the right-hand side says different from what I write on the left-hand side. So if you put in so instead of the only putting in the x, we put now in ix, and otherwise things remain the same. And then if we now compute this for a couple of terms, so for 0 we have something to the power of 0, which is always 1. Factorial of 0 is defined as 1, so we get 1 divided by 1, which is 1, so that's again the n0 term. Then the n1 term is ix to the power of 1 divided by factorial of 1, which is also 1, so we get ix divided by 1 factorial, okay, but can also just write 1. And then for n equals 2, we have x squared, which is the same as I squared x squared divided by 2 factorial, and so on. So here we have I3 x3 divided by 3 factorial, and so on. So we write up to n equals 4. And then the trick of the whole proof now is that we should have a closer look at what happens with our eyes here. So if we go from n to 0, 1, 2, and so on, first we have I to the power of 0, that was this case, which is 1, and I emphasize that it's positive here. Then we have I to the power of 1, which is also clear, and I emphasize only that it's positive, although, yeah, it's just an emphasis, so this plus there we could also, it would be maybe even better to not write that. I square, then you all know what's that? Exactly, teaching success. That's -1, and then I3, and this is why I had this plus there, is obviously I square times I, and this I square of course evaluates to -1, so we get -I. We have some dots here. -I. Yeah, because the square in there evaluates to -1, and then there's one I left. That's then -1. Let's go on. I4 is I square times I square, so that's -1 times -1, which is +1. So 1 essentially. I5 is then 1, which we've just seen here, times I, so that's plus I again. And it's kind of this recursive definition, essentially what happens here, but this has as a consequence that here, for example, we have I squared times I squared times I squared, which is I to the 6, and then if you have 2 i's being squared on the right hand side, or let's say an even number of i's on the right hand side here, then you get a positive number. If you, no, that was wrong. Now, if you on the right hand side have if you there have an even a number of i's, of course you get something. So if you have 2 i's or 4 i's, then you get something positive. But if you have a odd number of i's on the right side of these little I square, I to the power of n equations, then you get a negative, and sometimes you get I and sometimes you get -1. So in this case you would have I squared times I squared times I squared, which is -1 times -1, which is +1 times -1, and hence you get here -1. And for I7 you have I squared times I squared times I square, which are 6, and then you have another I, so you get -I. Yeah. So you have a pattern here which is not completely trivial, but it's not that complex neither. So you have 1, so you have +1, +i, -i, plus 1, plus I, -1, -i. Yeah. So what we now can do with our complex argument here, we actually can go on here. So of course we can split what we have here, so this thing, we can split that into, no, first we write it out actually. So we do 1 plus now our I to the power of 1 is I. So we actually get Ix divided by 1. And then our I square is -1, so we get a negative term. And for this we have x squared divided by and then our 3, we get a -i, so we get again a complex term, but this time with a negative sign. And for the 4, we get +1, so we have x4 divided by 4, and then I stopped. But yeah, so if you go over this again, yeah, just the only thing that happens is that this I to the power of something sometimes comes out I, sometimes comes out -i, sometimes comes out +1, and sometimes comes out -1. Now this is what we've written up, and now we split that into the into essentially even and odd terms, where we start with 1 and then take the remaining even terms. So that's x squared 2 factorial plus x4. So we are just rearranging the sum. Yeah, so we're just reordering what is above there, and we also realize that for the odd numbered ones, we have an I in front of them. Yeah, you also see that here. So here I to the power of 1 is 1, I to the power of 3 is -i, I to the power of 5 is +i, and I to the power of I to the 7 is -i. So the odd ones, which are the sign terms, get an I in front of them, and take this form, or not form, but we are now rearranging them into this. So the first one at least, x3, 3, x5, 5, that's an x, and so on. And then, of course, we are still interested in our cosine and sine definitions there. So then we realize that we can write the first thing here as the series with n going to infinity with the -1 n, and now there is another typo in the script because it needs to be x to the power of 2n, not x to the power of 2 times n, but it's just the n needs to be in the exponent, and we have 2n, so even numbers, so always read these 2n just as even numbers, then it's easier, so because you immediately see it, so 2, 4, these are all even numbers, so they play a role. And here we have odd numbers, so we have the same business again with the changing sign, so the minus or +1, and that's with the odd numbers, so 2n plus 1 divided by 2n plus 1. And these series terms are, of course, just the definition of the cosine and the sine. which then finishes the proof. So we do a little box here. So yeah, so it's a little bit nitty gritty, but and it's easy to go wrong because it's a sign, so in terms of positive or negative, not in terms of the function. So one needs to pay a little bit attention. If one memorizes that there are even and odd numbers with this 2n and 2n plus 1, that is actually quite or relatively straightforward. Maybe it's even better if you write out more terms here, then you can see it even better. Yeah, this is a little bit interesting, but essentially this thing here, so Euler's formula, just follows from these definitions here. Yeah, this is the whole message. Well, it's a little bit kind of a concentration game to go over this, but it's not, there's nothing completely outrageous in there. Good. So why did I go over that in that much detail? The reason is, again, that Euler's formula, so the relationship or the relationship between the exponential with a complex argument and cosine and plus I sine will come up many times. Okay? Euler's formula is now established and everybody should be happy with it. No? Good. Then we have a little bit of time to actually now establish the complex Fourier series, and I think this can be done. So the complex Fourier series, as I said in the very beginning today, this is just a rewrite of the real Fourier series. So we remind us briefly of the real Fourier series that we have a function f, which we can express in terms of this infinite sum of cosine and sine terms of varying frequencies. So we have ak cos, and then there's our omega k, and our omega k was defined as k divided by t x plus bk sine 2 pi k tx. And we discussed last time and also in the beginning today that these coefficients are given by these integrals. A0 is fx integrated. So if you looked into this protracted function stuff, you will also have found that this period t thing is not that crucial. Just that, yeah, you know that and don't worry about it. And the other ones are defined as the cosine. So fx times a cosine function of a given frequency. Maybe this is something I thought about this morning. To understand maybe a little bit what these coefficients mean, think a little bit at home about what it means that you multiply f with a cosine or sine of a given frequency, and in which sense this measures the covariation of fx and the cosine. So if you think about what you know about the correlation coefficient and how that is computed, think about it. You multiply them here and then you integrate over it. So of course these two things, so multiplying them and integrating, then you get a little bit of an intuition of what, in which sense this ak and bk measure the frequency contribution. The bk as this. So this is just what we did last time, just written up again and briefly discussed. One thing that I'm changing now is, because that's then more related to the Fourier transform and also how it looks in the complex Fourier series, I'm replacing this 2pk divided by tx by something else, namely first for k equals 1. So if you put 1 for k, then you of course get 2 pi divided by t x, and this I'm calling now omega 0, because this is kind of the first circular frequency that goes into the the first radio frequency, actually. The first radio frequency that goes into the whole thing. And it just makes things more concise, and that's how I find it in the books and so on. So it's just a notational change, which is a little bit annoying, but it's also not hard. So it just creates some work, but it's not hard to get. So we can now replace the 2 pi k tx by, so of course the same thing, k 2 pi divided by tx. And as we define this as omega 0, we can write this as k omega 0 x. So it gets a little bit less messy what we have in here, yeah. So that's one of the main points of this whole thing. We don't have 1, 2, 3, 4 symbols. We only have 3. Yeah, whatever. So it's just rewriting the inputs to the cosine and sine functions, which then means that the real Fourier series takes the following form. So with this little definition of omega 0 being 2 pi divided by the period of the function, we can also write the real form in this way.
Could you just go up 1 second?
No, because you have all of this in the script.
Okay.
So you don't need to write stuff down in here. There's no point in actually doing it, because it's all in the script. So I'm not writing anything that is not in the script. So, because it's, I don't know, it's just, you should actually, when you work on this material, write cover. So you should, what I'm doing to study things is to copy the book. Yeah, so you should sit down and write what I've written. You should write that again, and then you get familiar with that. In class, that's more like getting the general picture. This is what you should focus on, not so much the nitty-gritty details, although it's good if you can follow them, of course. Okay, so the main thing to now get this into a complex form is to use the Euler equations and Euler formula. Sorry, not the Euler equations. Don't know what that is. And to do that, the first thing to now translate this into what is called the complex Fourier series. One needs two equalities which follow directly from the Euler formulas, namely that cos x is e to the power of ix plus e to the power of minus ix divided by 2, and sine x is e to the power of ix minus ix, e to the power of minus ix. There's just one little typo. divided by 2i. Yeah, these follow directly from the Euler formulas and are shown in the script as proofs of 5.47 and 5.48 or analogously. So I will not go over how they follow, because if you have the script in front of you, you see that the whole thing just starts with the Euler formula and then needs 4 or so steps to go to these equations. So be happy with these equations. They just follow directly from Euler formulas. Now, with these expressions for cosine, and so maybe make this really explicit. So the only thing that happens here is that you solve the Euler formula for the cosine or the sine. Yeah. So if you solve this for cosine or sine, you get to this or that, which is not completely easy to see, but it can be seen after some time. I'm running out of time. Well, then instead of going into the complex form, we actually have a look at how these work, because I will not manage to get this in 9 minutes. So we have to postpone, sorry, timing didn't quite work, so we have to postpone the discussion of the complex Fourier form, but we can at least establish one or both of these here. So to see now how that happens, to fill the last 9 minutes and not run over time, we see the following. So we have the exponential of ix is cos x plus I sine x. So that's what we previously established. And this means that if we want to rearrange that for the cosine, then we have cosine x being, we just put the sine term on the other side, so we have exponential ix minus I sine x. That's something for a start. And then what we can do, and this is how this whole thing comes about, is that we add on both sides, we add x minus ix. Whatever. So what we do on both sides to establish this relationship is, minus sine x, so that's just what was there before, and then we add also the ix on this side. So this was newly added, but otherwise things were as before. And then we can expand this again in terms of Euler's formula. So that's now then cos x plus cos x minus x minus I sine, sorry, yeah. That's true. Minus I sine x. And here we actually have the same thing. So this is why I didn't want to go over them, because it's just, again, a little gritty and really not that interesting. So we have, on both sides, we have this minus I sine x term, which we can add on both sides, so we get rid of it. And we have 2 cos x here. And so if we add on both sides I sine x, it goes away. So we have x ix plus x minus ix, and then if we solve for the cosine term, we just have e. It's just a little bit shorter to write it with e in this case. Oops, we have e to the power of ix plus e to the power of minus ix divided by 2. So this is how this first equation comes about, and the second equation comes about actually in a very similar fashion. So yeah, so they really don't, and essentially we wouldn't have to discuss them. But the problem is if we, so the complex rewrite of the Fourier series uses tricks at multiple occasions, and I don't want to rush that. So that means that the next time we start from here, no, not from there, but from here, because we have now rewritten the real Fourier series in this manner, and we are happy with these two equations, so we can start there, and then rewrite the real Fourier series in the complex form. And then we can also, once we've done this, we this will shouldn't, I guess it will not take more than the first hour next time, but it takes a little bit because there are some little things where one needs to pay attention, and then we can discuss the polar form, and then we're done with the Fourier series and can do Fourier transforms. Yeah, so this was all a little bit nitty-gritty equation business. Other questions of some general things? It's all fairly straightforward. The reason why I'm going into the details of this is because if you've never seen these details, the relationship between exponential and cosine and sine will always feel like magic. And now they shouldn't feel like magic anymore, because you know that this is just happening because the exponential, the sine and the cosine are defined in terms of these series. These series are fairly similar to one another. So if one just puts a complex number in them, this relationship essentially falls right out of the similarity between the series in the first place. Then you don't, so because what we will see a lot is this kind of thing. And what you should actually also try to do is, if you see the things like sine, of course you have a picture in your head almost immediately of something like this. And this was somehow, this association was somehow formed in high school, and now I'm trying to, or you should try to form a new association that if you see something like this, so the exponential, a complex number, and an x in there, that you essentially also see something like this. And once you do that, then you're happy with it. Okay, so then I stop here, and it's complex Fourier series rewrite next time. Yeah? Good. Then let's have a break and start at 10 with the other course.